Same maze, same goal. 3 different brains race to escape. One spreads everywhere, one dives into trouble, and one guesses toward the exit.
That is the whole secret of pathfinding, choosing where to look next.
Now slow it down. The computer does not magically see the best route. It tests possible places, remembers what it learned, and avoids walls.
If the rule is good, the search feels smart instead of random.
First, we turn the world into something the algorithm can reason about. A messy world becomes a search graph. Each walkable cell is a node. Each legal move to a neighbor is an edge. Walls remove nodes or block edges.
Now the problem is not draw a path by eye. The problem is move through connected nodes until the goal is reached.
The search begins at the frontier. The frontier is the living edge of the search. Visited cells are places the algorithm already understands. Frontier cells are candidates waiting to be explored. Every algorithm has a different rule for picking from the frontier.
That one rule changes the entire personality of the search. A careful rule can make the search broad, deep, cheap, or goal-directed.
The simplest broad version is breadth-first search. Breadth-first search expands like an even wave. It checks every cell 1 step away, then 2 steps away, then 3. If every move has the same cost, this is powerful. The first time BFS reaches the goal, it has found a shortest path.
The price is that it may explore a lot of space in every direction. It is reliable, clear, and easy to understand. Depth-first search behaves very differently.
Depth-first search chooses a direction and keeps diving. It can run far down one corridor before trying another. That makes DFS useful for exploring structure or solving some mazes. But it does not naturally care about the shortest path. It may find a path quickly, or it may wander into a long detour. So DFS teaches an important lesson.
Finding a path and finding the best path are not the same thing.
Real maps are not always equal step grids. A road can be cheap, mud can be slow, and danger can be expensive.
Now, the shortest looking route may not be the cheapest route.
The algorithm has to care about total cost, not just number of steps. This changes the frontier rule. Instead of expanding evenly, we expand the cheapest known option first. That is the idea behind Dijkstra's algorithm. Dijkstra's algorithm keeps the best known cost to each cell. At every step, it expands the frontier cell with the lowest total cost so far. This creates a wave of price instead of a wave of distance. The wave bends around expensive terrain.
When Dijkstra finishes, it has guaranteed the cheapest path under those costs. But it does not know where the goal is pointing.
A heuristic gives the search a sense of direction. A heuristic is a useful guess. It estimates how far a cell is from the goal. The simplest example is straight line or grid distance. A heuristic does not replace real cost. It just helps the algorithm decide which frontier cells look promising.
A bad guess can mislead the search. A good guess makes the search feel much more focused.
A star combines 2 ideas. G is the cost from the start to the current cell. H is the estimated cost from the current cell to the goal. The score is F equals G plus H. That means a star remembers what it has paid and guesses what remains. With a good heuristic, it often explores far less than Dijkstra. This is why A star is common in games, robotics, and navigation demos.
Pathfinding becomes more interesting when the world changes. A new obstacle can block the route that looked best a moment ago.
The algorithm must search again or repair the old plan. In games, this happens when doors close or enemies move. In robots, this happens when a person steps into the hallway. The same core idea remains. Update the frontier and keep looking. After exploring, the algorithm still needs to draw the final route. Most searches store parent information. When a cell is reached, it remembers the previous cell that led there.
Those parent arrows do not look exciting at first, but they are the memory that makes the final path possible.
Once the goal is reached, we trace arrows backward to the start. Then the backward chain is flipped into a forward route. That is how exploration becomes a clean path. BFS, DFS, Dijkstra, and A* are not just names.
They are different answers to the same question. Which place should I look at next?
BFS says expand evenly. DFS says dive deeply. Dijkstra says choose the cheapest known cost. A* says choose cost so far plus a smart guess.